Welcome to the exciting world of Surds. In this course, we will delve into the fascinating realms of Surds and explore their operations and applications. Whether you are a student looking to strengthen your understanding of Surds, or you are an educator seeking to enhance your teaching skills, this course will provide you with a comprehensive foundation into these important mathematical concepts. Now, let's get into the lectures. Surds Lecture 1, Introduction. Before we understand vividly what surds are, we need to first understand the various types of numbers we have in mathematics. Now, we will delve into the various types of numbers so that we can now give you the general definition of what surds are. Now, types of numbers. The first types of numbers we have is the natural numbers. Natural numbers are set of counting numbers. Example 1, 2, 3, 4, 5, 6, and so on. All the numbers we use in counting are called natural numbers. They are the numbers we use in denoting positions, such as first position, second, third, fourth, and fifth, and the rest. So the numbers used in denoting positions are known as natural numbers. The natural number system is denoted by the Greek letter n. Take note of this. We have the second type of numbers known as the whole numbers. Whole numbers are a set of numbers including all the natural numbers and zero. Take note. The difference between natural numbers and whole numbers is that whole numbers includes zero. So the set of whole numbers are denoted by the letter W. We have the set of integers. Integers are a set of negative and positive whole numbers, including zero. The set of negative and positive whole numbers. Example of integers include -5, -4, -3, -2, -1, then 0, 1, 2, 3, 4, and so on. So the set of negative and positive whole numbers are known as what? Integers. So the set of integers are denoted by the Greek letter Z. We have the fourth type of number known as the rational numbers. Rational numbers are a set of numbers that can be represented in the form A over B. Take note. They can be represented in the form A over B, where A and B are both integers and B is not equal to 0. Because if B is equal to 0, the fraction becomes undefined. So example of rational numbers are, let's say 5 over 1, 1 over 2, 10 over 2, 2 over 7. Now you can see that this, for instance, let's use 2 over 7. You can see that 2 is a natural number, right? Or you can say it's an integer. Then 7 is also an integer. So the ratio of two integers is known as what? A rational number. So the set of rational numbers are denoted by the letter Q. There are other things I need you to know about rational numbers. Take note. The set of rational numbers, they terminate after some terms. And if they do not terminate, they usually have what we call repeated block. The set of rational numbers terminates after some terms, and if they do not terminate, they usually have repeated blocks. Now let me show you what I mean here. Now if you see this number, for instance, 1 over 2. 1 over 2 is a rational number, and 1 over 2 is what? 0.5, so it terminates. Another example, 1 over 4. This is a rational number, because we say a rational number is a fraction that consists of two integers. So 1 is an integer, 4 is an integer. So you can see now that 1 over 4 is equals to 0.25. So it terminates if you use your calculator to check that. Now, 26 over 7. Let's check it out. 26 over 7 does not terminate. With your calculator, you are going to see that 26 over 7 is 3.714285, 714285. That's how it continues. 714285, 714285, and so on. you can see that it has repeated block. Remember the definition. We said that rational numbers terminate after some terms, and if they don't terminate, they usually have what we call repeated block. So whenever you see a number that blows up, like 26/7, but it has a repeated block, then that number is what? A rational number. Example, 1/11. 1/11, if you check it out, it will give you 0.09090909 and so on. So you can see that these 09090909 are the repeated block. It therefore means that 1/11 is a rational number. Now, 10/3, for instance. 10/3 will give us 3.33333333 and so on. So you see, this number blows off. It doesn't terminate. But one of the distinguishing feature is that it has what? Repeated block. That means you can predict what is the next number. All these are examples of what? Rational numbers. Now let's look at the next type of numbers we have in mathematics, which is known as the set of irrational numbers. From the word irrational, it means something that doesn't make sense. So irrational numbers are numbers that do not truncate or terminate, and they do not have repeated block. So it means that the decimal digit continues without reoccurring. So it doesn't have any repeated block. These are irrational numbers. I want you to take note of this so that when I define surds, you'll be able to appreciate it. Now, example of irrational numbers, for instance, pi. The number pi, which you know, is 3.141592. You see, it blows up like that without any repetition. If you have a scientific calculator, press the number, the symbol pi, and press equal to, you will see that it blows up. It does not have a repeated block. So this is an example of an irrational number. Another one is square root of 3. Square root of 3 is 1.732050, and that is how it continues. It doesn't terminate, and it doesn't have a repeated block. Square root of 2, 1.4142135562, and so on. No repeated block. So these are examples of what? Irrational numbers. The set of irrational numbers are denoted by the letter IQ. Okay, now let's look at the other type of number system known as the real number system. Of course, the real number system are set of all possible numbers. It is made up of both the rational and irrational number system. So the set consisting of all the rationals and all the irrational numbers is known as what? The real number system. And it is usually denoted by the letter R. The last type of number system we have is known as the complex number system. Now, a very wonderful type of numbers. Now, these are set of numbers which are usually in the form a plus ib. A plus ib, where a and b are real numbers and I is equals to square root of -1 is an imaginary number. So this number system was discovered by a mathematician by name Euler, E-U-L-E-R. So these are set of numbers. They are always represented in this form. This is called the real part and this is called the imaginary part. So the complex number system are usually denoted by the symbol C. Now example, let me show you something. If you check square root of -4, square root of -4 is not defined. If you use your scientific calculator, you press square root of -4, it will show you mathematical error. But if you set your calculator to a complex mode, it will give you the answer as 2i. So to solve this problem, square root of -4 is equals to square root of -1 times square root of 4. And we have told you that square root of -1 here is what? Is I. So we can now say square root of 4 is what? 2. And then square root of -1 is I. So the answer to square root of -4 is what? I2, which is the same thing as what? 2i. I hope you understand that. Okay, let's take another example. Square root of -16. To solve this, this is equals to square root of -1 times square root of 16. Of course, square root of minus 1 is what? I. And square root of 16 is what? 4. So that will give us I4. So the solution to square root of minus 16 is what? 4I. This is an example of complex numbers. Okay, now let's look at the definition of surds. I told you earlier that before we delve into the concept of surds, you need to understand the 7 types of number system we have. So having understood that, now what are surds? We say that surds are irrational numbers, note the word, irrational numbers, which are in the form of roots. That means any irrational number that is in the form of roots, that they have square root, cube root, and the rest of the thing, they are called what? Surds. Example of surds are square root of 2, square root of 5, square root of 3, square root of 11, etc. Because if you check this with your calculator, they are going to give you numbers that do not truncate, and they have what? They do not have repeated block. That's why they are called surds. But numbers like square root of 4 is 2. So this is a rational number. It's not a surd. Square root of 9 is 3. So it's not a surd. Square root of 16 is what? 4. It's not a surd. Because they can be simplified to obtain rational numbers. So please take note of this definition. Surds are irrational numbers which are in the form of roots. What are irrational numbers? Numbers that do not truncate and do not have what? Repeated block. That's as simple as that. So we can say numbers that do not make sense. Okay, now another definition I want you to note before we go into the wall of surds is that I want you to note that 2 or more surds are said to be like surds or similar surds if and only if the number under the square root sign are the same. So when do we say that 2 surds are equal? When do we say that 2 surds are like? When do we say that 2 surds are similar? It is only when the number under the root sign are the same. For instance, square root of 5, 6 root 5, and 12 root 5, then 7 root 5 over 3 are all what? Like surds. Why are they like surds? Because under the square root sign here there is 5, under the square root sign here there is 5, under the square root sign here there is 5, under the square root sign here is what? 5. So 2 or more surds are said to be like surds or similar surds if the number under the square root sign are equal. Take another classical example. I want you to note this. 5 root 3 and 3 root 5 are not like surds. Why? The number under the square root sign here is 3. The number under the square root sign here is what? 5. So they are not like surds. So they are not like surds because the number under the square root sign are not the same. I want you to take note of this. Because when we are solving problems involving additions and subtractions of surds, if you don't understand the concept of like surds, you are going to have difficulties. Okay, let's proceed. Now we have some rules for simplifying surds. Rules for simplifying surds. Very, very important concepts. Now, the following are the basic rules that are commonly used when performing operations on surds. Look at the rules here. The first rule states that square root of m times n, you can split it to have square root of m times square root of n. Very important. These rules are true and can be verified. Square root of m divided by n, you can split it to have square root of m all over square root of n. This is very true. The third rule, square root of m plus n is not equal to, that means you cannot split it to get, you cannot say square root of m plus n is equal to square root of m plus square root of n. That's wrong. Square root of m plus n is not equal to square root of m plus square root of n. Take note of this. Now, square root of m minus n is not equal to square root of m minus square root of n. You may be asking me why. Don't worry. You are going to verify it on your own. I'll tell you what to do so that you can know that these rules are actually true. Now, the fifth rule I want you to note, this rule is very important. A root m is the same thing. That means is equal to square root of. Now when you push this a inside the root sign, it will become a square then times m. Take note, a root m is equal to square root of a square times m, because this was a square root. So when this a is pushed in here, it takes a raised to the power of 2, because originally a raised to the power of 2 gave us what? A. Take note. Now the sixth rule, a cube root of m is equal to, now when I push this a inside the root sign, it becomes a cube times m. Take note of these rules. A cube root of m is equals to the cube root of a raised to the power of 3 times m. These are the basic rules commonly used when performing operation using sort. I said note that the above rules can be verified using numbers. And I think that's what I'm going to give you as a leisure work. Okay, we have come to the end of this introductory section to the concept of sorts. Now, I want you to verify the following laws of sorts using the values m equals to 9, n equals to 4, and a equals to 2. Now, these are the rules. All I want you to do is simply replace any place you see m, you replace it with 9. Any place you see n, replace it with 4, so that when you do that, you solve the left hand side, solve the right hand side, you are going to discover that the rules here are true. Please do that and get back to us. Thank you for your attention. In our next lecture, we are going to be considering sort lecture 2. Here we are going to be looking at the concept of simplifying sorts. See you in our next lecture. Thank you for your attention.